In Module 1, 1.1 and 1.2, I introduced the concept of reliability, why failures occur, and how uncertainty in load and strength cause failures to occur, and how strength degrades. And I then went through a detailed case study of reliability analysis, reliability characterization on a real product from my research. So, starting with this lecture, I'm going to get into the math that we would need to characterize the reliability. So, we'll start with Module 2.1, which is probability rules. Module 2 would be basic probability, if you will. And then we will go on to expectation and variance in Modules 3 and its submodules. And then go on to, in Module 4, we'll go on to this. You're looking at an application. In Module 4 will be normal distribution and then an application of normal distribution in load strength interference. So we'll start with probability rules. So why do we need to study probability? So the reliability, quantitative characterization of reliability relies on the math of probability and statistics. And we will cover in this course. So this is not a statistics course. We will only study the statistics that we need to characterize reliability. So we will cover continuous functions, functions of time. So we will talk about something called cumulative distribution function, which is a statistical concept. But from a reliability point of view, its importance is that it characterizes the fraction of components that have failed at a given instant in time. So I start with 100 parts, I put them through test, and they start to fail. I track the failure with time, the fraction that has failed out of the 100. Okay, let's say 30 parts have failed out of 100. So then fraction failed is 0.3. Reliability turns out to be the complement of fraction that has failed, which is really the fraction that has survived. So if 0.3 is fraction failed, reliability would be 0.7. We'll also learn about something called hazard rate. These are all continuous functions of time. And we'll often, as we will learn later, we will treat time as the uncertain parameter. So in other words, same component, I test it multiple times, and I get different times to failure. So the times to failure is my uncertainty. We will also study discrete functions, or two-state discrete systems, pass, fail, working, not working. We'll do this primarily through binomial and Poisson distributions. The continuous functions, we will learn about normal distribution, log normal distribution, Weibull distribution, primarily, exponential distribution in between. So we will start with basic definitions of probability. We'll go through basic probability rules. Next, we will do conditional probability before we go on to continuous random variables, expectation and variance, and so on. So for our purposes, statistical methods provide the means for analyzing and understanding and controlling variation. As I described in the case study, there are always two aspects to characterizing reliability. One is a statistical aspect, the other is physics of failure, and both have to go hand in hand. One is insufficient by itself, but our focus in this class will be more on the statistical methods, because physics of failure often requires advanced knowledge that will be gained in advanced classes, typically physics-oriented classes. So we'll start by defining probability. So there are two definitions that I will give you. This is the first definition. This is definition number 1. So if an event can occur in a total of n possible ways, and if you have an event A, and that can happen only in little n of these ways, then the probability of A occurring is n over n. little n over cap n. Example, I do a coin toss. I can get either a head or a tail. So cap n is 2. And let's say event A is the event that the coin toss results in a tail. Then probability of A would be, there's only one way you can have a tail. So the probability of getting a tail is 1 over 2. So that's the definition of one definition of probability. We know the total number of outcomes here. We know exactly the total number of outcomes. Okay. And we then ask the question, what's the probability of a specific event which describes a small n outcome? So the key point here is total n is known. In definition 2, total n is not known precisely, but it's a sample. The situation we might find ourselves in reliability characterization, we don't test infinite number of components. We only test a finite number of components, n components, cap n components, and we find failure in little n times. So in this particular case, we have a sample of n components or n experiments. This is a sample. It's not the whole of the population. And then we can define the probability of an event A occurring is limit as n tends to infinity, little n over cap n. So if this limit will give the probability of event A occurring. So this is again valid in situations where we might be testing a sample of a larger population. Now, anytime you have a sample, the sample selection has an influence on your predicted probability. If, for instance, I test 10 parts and I find 3 parts to be defective, out of these 10 parts, 3 were defective, and therefore I would say if defect rate is 30%, 3 out of 10. And now if I have the next 10 parts, I might say it's 20%. There is sample to sample variability. And together I might say, these two together, I would say 5 out of 20, and that's 25%. So there is significant sample size dependency of the failures, particularly when you have small number of samples. So your prediction might depend on the sample size, and so therefore the degree of confidence on the statistics of failure depends on the sample size. That's a key point to remember. Whenever we do statistical characterization, there's always a dependency on sample size. Any statistical characterization requires, for us to have greater confidence, it needs to have sample size approaching infinity. So anytime I have a sample, I need to have as large a sample as possible. So that is the sample size dependence. Now what we are going to do is to learn basic probability rules as well as some notations. So we've already discussed probability of obtaining an outcome A is defined as P of A. And if I had an outcome B, then I would be P of B. So let's say the joint probability that an event A and B occur. Let's say there are 2 events. A might represent probability of coin toss resulting in a tail, and B might represent the event that the coin toss results in heads. So A represents the event that coin toss results in tail, and B might represent coin toss results in head. Then we can ask the question, what's the probability that A and B will occur together? In this case, it's not, they are mutually exclusive, but in general we'll denote if these 2 events were not mutually exclusive. So then what's the probability that A and B will occur? And it's denoted by probability of AB or probability of A intersection B. We will follow in this class as much as possible the set notation. Okay, so we'll use this notation, but this is also a common notation. Similarly, this is if the probability that A and B will occur. So this conjunction and is critical here. So whenever you see and, it means product of A and B or A intersection B in set notation. That's a key connection that you need to make. Similarly, the probability that A or B, an event A or event B occurs, is denoted by probability of A plus B or A union B. Again, this is the notation, set notation, that we will try to use as much as possible. We will not use this notation as much. Okay, so these are all some basic definitions here, notations here, if you will. We haven't defined any of these probabilities. We'll define them next, but these are some basic notations. The conditional probability of obtaining outcome A given that B has occurred is denoted as probability of A given B. It's to be read as A, probability of A given B. So that's called conditional probability. So we know some information ahead of time that B has occurred. Then we ask the question, what's the probability that A will occur given that B has occurred? So that probability is to be read as probability A given B. Okay, so we're all defining some notations here. We haven't quite gone in detail. Similarly, we are going to define what's called a complement. So if I have an event A and the probability of event A occurring is P of A, its complement, that is A not occurring, is denoted as A bar or A complement. Is probability of A complement is 1 minus probability of A. That's the definition of complement. The joint probability that A, now we are going to define this product A and B. The joint probability that A and B occur is denoted by, as we said before, probability of AB or A intersection B. We will use this more. So if the events are independent, in other words, occurrence of A does not influence occurrence of B. For instance, A might correspond to obtaining a tail in the first coin toss, first of two coin tosses. B might correspond to occurring a tail in the second of the two coin tosses. So then A and B would be typically independent because the probability of obtaining a tail in the first coin toss does not influence the probability of obtaining a tail in the second coin toss. Then we would say those two are independent events. So probability of A and B, so I'll read this as A intersection B is the same as A and B, is probability of A times probability of B if the two events are independent. So similarly, addition rule, probability of A or B or A union B. And in order to reason through these expressions, we will use the Venn diagram. Venn diagrams are very convenient to reason through these addition expressions. So probability of A or B, A union B is A or B, is probability of A plus probability of B minus the intersection region, because that would have been counted twice. So you would have to subtract the intersection region in order to get the probability of A or B, which represents the area inside this region here. Since when we count probability of A, you would have this intersection region once. When you count again, when you add to it probability of B, you've added this intersection region one more time. So you have to subtract that in order for you to get the area inside this union of these two regions, A and B. Again, if A and B are independent events, we learned that the product A and B or A intersection B reduces to probability of A times probability of B if the two events are independent. I talked about two coin tosses, first coin toss resulting in a tail and second coin toss resulting in a tail. The probability of A and B is probability of A times probability of B, 1/2 times 1/2, 1/4. Okay, so this follows from Venn diagram. And only thing we've done here is we've used the fact that A and B are independent events. If A and B are independent events, we can replace A intersection B with probability of A times probability of B. If they are mutually exclusive events, so I have a coin toss, A is the event that in that coin toss I get tail, B is the event that in that coin toss I get a head. Then in single coin toss, I cannot have A and B. Probability is 0. And therefore, A or B is probability of A plus probability of B. Okay, in this case, it'll be probability of head. In this simple example that I gave, it's a probability of tails plus probability of heads, which is 1. A or B is 1 in this case. De Morgan's law allows us to estimate the probability of A not occurring and B not occurring. That's very convenient. You'll find that this is a much more convenient way to define some events. So A not occurring and B not occurring is really the region which is outside the region, the union region here. The region outside of that is, so A not occurring is everything outside of A, B not occurring is everything outside of B. And so if I take the intersection of those two, what I would get is the region outside of this region that I'm showing. And that is nothing but A union B not occurring. Just simply from Venn diagram, probability of A union B is the region inside the two circles, and complement of that is the region outside of the two circles, and that is what this formula is. And complement of A union B is 1 minus the probability of A union B. Okay, so De Morgan's law is very convenient. And you can extend this addition rule to other more number of events, A, B, C, D, and etc., etc. It's more complicated, but its formula essentially, you can reason through this purely geometrically using the Venn diagram. So probability of A or B or C occurring. Let's say A, B, C are 3 events. Probability of A occurring or B occurring or C occurring. Okay. So A occurring probability is denoted by the circle, B occurring is denoted by the circle, C occurring is denoted by the circle. A or B or C means that event is within the region enclosed by these 3 circles. The union of these 3 is probability of A, this circle region added. Okay, but when we and plus this circular region added, when we do that, we would have double counted these intersection regions, AB intersection region, BC intersection region, and AC intersection region. So we'll have to subtract them. But in doing so, we would have actually eliminated the common intersection region, which we need to add back. So that is plus probability of A intersection B intersection C. So those are the probability rules. And this is module 2.1. So in module 2.2, what I will do is I'll work out some example problems to put to practice these probability rules.